Hi. So first of all, I would like to thank the organizers for giving me this opportunity to present my work here. In this talk, I will present one of my recent works where with two of my collaborators, I have explored the aspects of dark matter freezing in an effective field theory framework. So let us begin. So this is a rough plan of the talk where I shall start with the canonical WIMP scenario and try to point out some of its drawbacks. Then I will introduce freeze-in as an alternative to freeze-out that can also account for the observed dark matter abundance. Then I will jump into my own work itself, which is the effective theory of dark matter and freeze-in, and where I shall talk about the relevant operators that we have worked with and how we computed the dark matter yield from annihilation and decay channels. And then I will point out a scenario where it is possible to compare the effective theory scale with the neutrino mass generation scale. And then I will briefly talk about how the dark matter can be produced from the radiative inflaton decay in this framework. And then I will end with some concluding remarks. So this is the canonical story for dark matter. The standard law is that the dark matter was in equilibrium with the thermal bath at very early universe when its interaction rate with thermal bath was much higher than the expansion rate. Then the dark matter will keep track its equilibrium abundance as long as the reaction which keep the particle in chemical equilibrium can proceed rapidly enough. By rapidly enough, we mean that the time scale more rapid than the expansion rate of the universe. So the dark matter number density would have gone down to zero if it would have kept following the equilibrium abundance. But before that really occurs, then freeze out happens, or in other words, the reaction rate falls below the expansion rate, and thereafter the yield is constant. Thus, this is called freeze out. And the dark matter energy density after that is redshifted as a negative third power of the scale factor, and eventually this dominates over the radiation density. This is what we exactly see in the plot over here, which can be obtained by solving the Boltzmann equation. Here, this black solid line, it corresponds to the equilibrium number density that of course goes down to zero. And all these dashed lines, they correspond to different freezing corresponding to different value of this thermally average cross section sigma v, which actually carries all the information of the standard model of the dark matter model underlying. And the parts of having such a vanilla WIMP scenario is something called the WIMP miracle, where we can show that the contribution to relic abundance from thermal WIMP is roughly independent of its mass and depends only upon the annihilation cross section. And the cross section is of the order of the weak scale, which means that the scale of the annihilation cross section is related to a known mass scale. So this is something interesting, as this indicates the presence of new physics at around TV scale that is within the reach of different experiments. Now the problem comes mainly from dark matter direct search, where we look for excess in the recoil rate in scattering experiments for such WIMP scenario. And unfortunately, as we can see from this summary plot, there's no significant excess we have found so far. All we have found are the exclusion limits, and this essentially constrains the dark matter mass and its interaction cross section to a great extent. On the other hand, in collider experiments as well, we have not seen some significant excess in terms of the missing energy that can account for some new invisible particle at around TeV scale. So together, it seems that the WIMP paradigm is not working well, and there is a need of paradigm shift. Instead of a thermal WIMP, therefore, where the dark matter is assumed to be in equilibrium with the standard model in the universe, and finally decouples to produce the observed abundance, we can think of a scenario which is complementary to this. In other words, we can have a situation where the dark matter couples to the standard model very weakly, or the coupling is so tiny that the dark matter can never come in equilibrium with the standard model path, and therefore it is not possible for the dark matter to freeze out. Instead, it can be produced from the particles within the path itself that are in equilibrium, and this is something we call as freezing. There are of course other scenarios or other mechanisms of accounting for such excuse me, non-thermal production of dark matter, which are called WIMP-ZILAs or SIMP or ELDER, and each of them are different and they have different phenomenological outcome. Now, the basic assumption of having a freezing dark matter yield is to assume that the dark matter number density is zero or extremely small at the early universe. Now, this may result from the reheating itself when the inflaton decays significantly to the visible sector, or maybe some other mechanism which we are not aware of. Now, as I mentioned that because the dark matter coupling with the visible sector is super small, it is not possible for the dark matter to be in equilibrium with the standard model path. But since the coupling, however small, is still non-zero, so the bark particles can produce the dark matter from decay or the annihilation. And dark matter number thus keeps building up as long as the particle from which it is getting produced is not Boltzmann suppressed. So this sort of the usual fusion setup. Now, broadly speaking, there are two classes of fusion as well. One is called the IR fusion, the other one is called the UV fusion. So we'll go through it real quick. So in IR fusion scenario, the dark sector and the visible sector, they are coupled via renormalizable interaction like this one. In that case, the dark matter yield is maximum at the low temperature, essentially at around the mass scale itself, because below which it suffers from the Boltzmann suppression. And the coupling has to have the order of 10 to the power minus 10 or so, which is very small, such that it ensures the dark matter is produced non-thermally or it is out of equilibrium. And the caveat in such a case is that one cannot really account for such a small coupling. However, one can say that within the standard model itself, there is a huge hierarchy in the Yukawa sector, but even that is very unnatural. On the other hand, if the two sectors are connected via some non-renormalizable interaction, for example, some 1 by lambda interaction, which is of course larger than a dimension 4 interaction, then it can be shown that the dark matter yield is directly proportional to the temperature itself. So the yield maximizes at a very large temperature, which we shall refer to as the reheat temperature of the universe. Of course, maximum temperature can be much larger than the reheat temperature itself, but just for the sake of simplicity, we will talk about the heat temperature. And you can see the difference from this plot as well, where you can see for UV fusion, the yield builds up very fast and becomes constant at a very large temperature at around the reheat temperature itself. While for the UV case, the yield builds up very slowly and the fusion happens at a much later time at a low temperature. So that is why it is called IR. Now, in our framework, what we have is a singlet Majorana fermion that we will call as a dark matter. And since it does not have any tree-level coupling with the standard model, so the only way to couple this in such a case is via some non-renormalizable interaction. And we also impose a Z2 symmetry, which we assume to remain unbroken, such that it can stabilize the dark matter itself. And since in this case the dark matter is Majorana, which means that it is its own antiparticle, so we do not have this vector current or the dipole moments, or only we have the scalar side pseudoscalar axial vector dark matter bilinears. And we assume that these operators that we will write are in the unbroken electroweak phase basis, and all our ignorances are dumped within this cutoff scale lambda, and there are no other parameters. And for simplicity, although we will tabulate all such operators, but for simplicity of the analysis, we will stick to scalar operators itself. However, taking other interaction, for example, like pseudoscalar axial vector interaction, will not going to change our conclusion much. And of course, in all cases, we will assume that this lambda is much larger than the dark matter mass and the heat temperature, just to ensure that the EFT limit is valid. Now, we can actually tabulate the relevant operators that can give rise to the dark matter interaction with the standard model. As I mentioned, that we list all sort of interaction that can occur for a gauge singlet Majorana field. Our only guiding symmetry is the standard model gauge symmetry, which we assume to remain unbroken. And then there is, of course, a Z2 symmetry that keeps the dark matter stabilized. Now, there is one more hurdle that concerns the number of operators. As we can see that beyond dimension 5, there are a huge number of standard model gauge invariant operators. So for the sake of simplicity, we will go up to dimension 5 in the standard model sector, while since scalar operators can make up to dimension 3, so together we will have dimension 8 operators at best. So we actually list operators up to dimension 8 that will contain the standard model and the dark matter operators taken together into account. So this is the resulting Lagrangian, where we have the tree-level standard model field or the Lagrangian and the tree-level dark matter interaction, and then we have all those operators up to and including dimension 8 that corresponds to dark matter standard model. Here we see that there are different fields that arise. For example, the dimension 5 being the simplest, which has the standard model Higgs field bilinear. And then in dimension 7, a host of interaction appears in terms of the standard model gauge bosons or standard model fermions taken into account, while in dimension 5 we have only one operator, which is the gauge invariant Weinberg operator that can also account for the neutrino mass. On the other hand, for uh, axial vector interaction, because of the presence of this gamma mu, we have to make this operator load in singlet. So therefore, we have all those gamma mu and dbu interactions within the standard model sector. Now we can proceed to find the dark matter yield by solving the Boltzmann equation, considering different scattering and decay channels that can occur before and after the electroweak symmetry breaking. And as we can see that before the electroweak symmetry breaking, there can be numerous multi-particle channels, for example, 2 going to 2 or 3 going to 2 or 4 going to 2, etc. While after symmetry breaking, on top of these 2 going to 2 channels, we also have the 1 going to 2 channel that corresponds to the decay. Of course, the decay is possible only when it is kinematically allowed, which means that the dark matter mass is less than half of the mass of the Higgs. And as you can see that we will compute all these channels before symmetry breaking, while after symmetry breaking we have only 2 going to 2 channels, because after symmetry breaking the standard model particles are massive itself. So therefore there is a mass suppression from the propagator, and also as they all of them are massive, so we can assume that all such 3 to 2 or 4 to 2 channels are subdominant, corresponding to in comparison to the 2 to 2 channels. And before electroweak symmetry breaking or after electroweak symmetry breaking, in both cases, irrespective of the era, the dark matter can be massive because it has a non-zero Majorana mass term. However, the standard model particles becomes massive only after the symmetry is broken. However, before symmetry breaking, as the reheat temperature is very high, we can assume all the particles, including dark matter, to be massless, and that does not affect the result. So there is one constant on the cutoff scale lambda that inevitably arises from the condition of dark matter being produced out of equilibrium from the thermal path. This we can find by comparing the reaction rate with the expansion rate, that is here. This gamma is the reaction rate, of course. And here we can see these different lines, they correspond to different operators of different dimension. For example, this blue line corresponds to dimension 8, and this red line corresponds to dimension 5. And these contours, they actually correspond to r equal to 1. So as expected that for larger dimension, the bound on lambda is basically loose. On this plot, we also show the region where the where it's possible that the EFT theory will be broken down because this cutoff scale becomes lower than the temperature of thermal bath. So we have to keep in mind that this bound on lambda is always satisfied such that we can ensure the non-thermal production of the dark matter via freezing. Now we can obtain the dark matter relic abundance from the yield and constrain the resulting parameter space. Here, just to clarify that we have three free parameters: the dark matter mass, of course the cutoff scale lambda, and then the reheat temperature. As the bound of the reheat temperature is very loose, as we can see from here, from PBN, and from the upper limit comes from the gravitino production, while this can be much larger in a non-supersymmetric case, for example in a general inflationary scenario. Here we see some interesting features in the lambda versus TRH plane. So this is the parameter space that satisfies relic abundance. This is for a dark matter mass 50 GeV, such that the decay from Higgs, the on-shell decay from Higgs, is possible. So we can see that for a lower T reheat, so this region is IR dominated, while as we keep increasing the reheat temperature, there is a linear rise which corresponds to the UV domination. But this feature, this tail, is not exactly seen here, where the dark matter mass is larger than the electroweak temperature itself. So most of the contribution comes from the UV region, while this tail can be seen even if we go below a TeV for the reheat temperature itself, which we do not see here. So the point is that for a massive dark matter, most of the contribution comes from the UV region, while for a lower mass dark matter, specifically for a dark matter mass below the electroweak phase transition temperature, there can be a contribution both from UV and from the IR dominated processes itself. And now we will make a connection with the neutrino mass scale. So this connection in a simple EFT setup is not very prominent, or rather sort of convoluted. What the point here is that the scale of the lepton number violating dimension 5 and dimension 7 operators, for example, these two operators that can give rise to right neutrino mass, they can coincide with the freezing scale that gives rise to correct relic abundance for operators of the same dimension, that is dimension 5 and dimension 7. So in these two plots, we see that this red colored region is the region that satisfies relic abundance from dark matter freezing, while this dashed line, they correspond to the minimum neutrino, minimum scale that can produce the right neutrino mass. So region above these dashed lines, they satisfy both relic abundance and neutrino mass in both of these two cases. So the point here that we want to make is that we can probe the freezing scale from the neutrino mass scale itself, which gives us a handle for an observation of what dark matter production via freezing. Okay, and then in this slide we show that even if there is no direct coupling of the dark matter with the inflaton, but still the dark matter can be produced from the inflaton decay, where the decay can happen via the Higgs loop. Here we see that in order to produce such dark matter from the inflaton decay, the branching ratio has to be very small, but we allow a very small branching for the inflaton to decay invisibly to dark matter. However, we have to confirm or make sure that still the dark matter has some interaction with the Higgs. For example, in this case, is the dimension 5 operator that makes the connection. Here we see that in such a case where the dark matter can be produced from the inflaton decay, all of the dark matter relic abundance can be generated, and the branching ratio has to be kept small, as I was saying, in order to avoid the overabundance. And in this case, we can actually produce the observed abundance even for a lower scale lambda than what is required for production from a dimension 5 interaction. So the bottom line is that even if there is no direct connection with the dark matter with the inflaton, but still if there is a sort of dimension 5 interaction between the dark matter and the standard model, then we can produce this dark matter from the inflaton decay itself, which also corresponds to freezing scenario. So in conclusion, we provided a very simplest possible operators connecting the dark matter to the standard model relevant for freezing scenario up to and including dimension 8, where we have constrained both the cutoff scale and the reheat temperature from the requirement of producing correct relic abundance. We tried to make a connection between the cutoff scale that can produce right relic abundance with the neutrino mass generation scale, although this is not very prominent here, which can be made more profound in UV complete setup. And we also showed that it's possible for the dark matter to be produced from the inflaton decay, even if it is there, even if there is no direct connection between the two. And maybe in a more UV complete scenario, one can make a connection between the inflation and the freezing, which can give rise to some interesting setup. So that's all from my side. Thank you so much.